Okay, before we get started on today's topic, it's worth noting that some of the history of what I've been saying about Galileo actually comes from this excellent book by Thomas Kuhn, The Copernican Revolution. Now, Thomas Kuhn is most famous for the book he wrote after this, The Structure of Scientific Revolutions. And The Structure of Scientific Revolutions is one of those books that inspired pretty much every stupid social science and humanities major in the 1990s to run around saying that science is just like one paradigm, man, and it's been shown by Kuhn that like science goes through these paradigm shifts, and so what's considered objective truth in one time is not objective truth in another. So all of this is just like your perspective. Those people are idiots. And The Structure of Scientific Revolutions is actually not a bad book. In fact, it's an inoffensive book, but it's an inoffensive book that lent itself to being misconstrued. This book, written before it, doesn't have that problem. Nobody's ever run around quoting the Copernican Revolution as proof that science is all just like your opinion, man. So frankly, I wouldn't be surprised if most of the people who think that the structure of scientific revolutions prove that science is just like your opinion are unaware that Kuhn actually wrote the Copernican Revolution. But he did write the Copernican Revolution. It provides a lot of fascinating material on Galileo and absolutely everyone who came before him, even the most obscure. And with that, let us start today's topic. So let me pull up the lecture slides. I'm going to actually start with a few things. Oh, there's some sort of notification. Why is Zoom giving me a notification? Okay, not sure why Zoom is doing that, but okay. All right. Anyway, we're going to start by finishing up some stuff from last time. I want to go over another example or two with space-time interval. So let's say that we have some hypothetical particles with a half-life of 2 microseconds, and they go from point A to point B over a distance of 2 kilometers. That would be a linear accelerator, something that speeds up particles and shoots them in a straight line. Linear accelerators actually get used a lot in research. There's the Stanford Linear Accelerator used to accelerate particles to very high energies and look for new physics. There are smaller linear accelerators used to make medical isotopes. And by the way, there's a common type of dilettante who likes to go around claiming that Einstein was wrong. The way we know Einstein was right is that on a daily basis, people use relativity for things like GPS, which we'll get to at the end of the semester, or making isotopes, running nuclear reactors, accelerating neutrons, so that producing neutrons in nuclear reactions and then slamming them into targets, not so we can study really exotic physics, but so that we can study the structure of materials by bouncing neutrons off of them. Or people who make isotopes for medical use by accelerating particles to high speed, slamming them into other particles and producing nuclear reactions that result in whatever isotope they need so that you can get a diagnostic test. So on a daily basis, people use relativity for very practical things, and it works. So here's a linear accelerator. It's 2 kilometers long. That wouldn't be a hospital linear accelerator, but maybe a research grade one. And the particles have a half-life of 2 microseconds. And what we want to figure out is, in the reference frame of the particles, how much time does it take to get from point A to point B? In the reference frame of the ground, if they're going at 0.866 times the speed of light, well, delta x over delta x over the velocity would be delta t, or 2 times 10 to the third over 0.866 times 3 times 10 to the eighth. That's 8 microseconds. That's 4 half-lives. So after 4 half-lives, we'd be getting half of half of half of half, 2 to the fourth, or 1/16 of the particles will survive that trip. But if we look here, the space-time interval, which is the time detected by a particle that was present at this event when the particles leave point A, present at this event where the particles arrive at point B, and traveling at constant velocity between them, so it's in an inertial frame, that's going to be delta t squared minus square root of delta t squared minus delta x squared. And so if we plug in, we get 3.94 microseconds, or very, very close to 2 half-lives. So if 2 half-lives elapse, then we get half of half, or a quarter of the particles. Any questions on how I did that? Remember, the time observed by someone in an inertial frame present at both events is the space-time interval. It's defined by this formula. Now, let's go through another example, one from the book and the problems at the end of chapter 3, problem R3, R2. It says that your boss is on a shuttle going from Earth to Pluto at 0.6 times the speed of light. And once your boss is an hour into the flight, according to your boss's watch, not according to your watch, according to your boss's watch, your boss sends you a message asking you to give him a wake-up call in an hour. You receive the message, you send back a reply. And the question is, when does your boss receive the reply? All right? So that's a lot of words to translate into numbers and symbols and diagrams. If we look at this diagram, well, we've got the world line of light, okay? And we just put that there for reference. We've got the world line of the ship moving at 0.6 times the speed of light. Now, when it sends out light, that's going to go at the speed of light. And so that line is going to have a different slope. And then your reply is also going to have a different slope than the ship's world line. So the first thing we have to do is we have to figure out, when did your boss send you that signal? According to your boss, of course, it was an hour into things. But that's not how long it takes according to you, because you were not present at events A and B. Event A is when your boss leaves Earth, and event B is when your boss sends the signal. You're present at event A, but you aren't present at event B. Your boss is present at event B. So your boss measures a space-time interval, which is the time elapsed squared minus the distance squared. And we don't know the time elapsed, nor do we know the distance. Okay, these are two unknowns. But we know that how far your boss was from Earth when he sent the signal is V delta T. So we know that 1 hour is equal to the square root of T squared minus V squared T squared. We can factor out that T. That's T Earth means that that's a time measured in the Earth's reference frame. That's T Earth square root of 1 minus V squared, or T Earth square root of 1 minus 0.36, because the speed is 0.6. It's 0.8 T Earth equals 1 hour. So we divide both sides by 0.8 and we get 1.25 hours. So the ship is 0.75 hours from Earth. So then we have to figure out when you receive that signal. Well, you receive that signal after the light has traveled a distance of 3/4 of a light hour. So that's 3/4 of an hour later. So now 2 hours have elapsed in your reference frame since you sent, since your boss left Earth. You send a reply. Now the reply is traveling relative to you at the speed of light, and your boss is traveling relative to you at 0.6 times the speed of light. And we have to figure out when your boss gets that signal. So to do that, we just figure out, where does the world line of your boss intersect with the world line of that signal? Well, the world line of your boss is just 0.6 multiplied by t. That's the coordinate of your boss, because your boss has been going at constant velocity since t equals 0. The world line of the light, well, it's got slope 1 because it's light, but it didn't leave at t equals 0. It left at t equals 2. So the distance traveled is t minus 2. So that is the world line of the light. And these two have to be equal to each other. The coordinate of the light has to be equal to the coordinate of the boss when the boss receives the signal. So 0.4 times t Earth, if we just do some subtraction, equals 2. T Earth equals 2 over 0.4, or 5 hours. So your boss has been traveling for 5 hours. He's 3 light hours away from Earth because he's going at a speed of 0.6. So then we have to figure out how much time has elapsed in your boss's reference frame between when your boss sent the signal and when your boss received your reply. And again, your boss is in an inertial reference frame. That in and of itself doesn't matter too much because lots of people are in inertial reference frames. But your boss was also present at events B and D. And events B and D, well, let's see here. Their difference in time is 5 minus 1 is 5 minus 1.25. And the difference in distance is 3 minus 0.75. So we could do it that way. Or we could figure out, according to your boss, how much time has elapsed since leaving Earth. And that's going to be square root of 5 squared minus 3 squared, because the time is 5, according to you, and the distance is 3, according to you. So on your boss's ship, 4 hours have passed since leaving Earth. And your boss sent the message when only 1 hour had elapsed since leaving Earth. So your boss has been napping for 3 hours in his reference frame. Any questions? Anyone? One thing that's important to understand is that when I say that 3 hours have elapsed on your boss's ship and a different amount of time has elapsed according to you, this isn't just some trick of when signals arrive, so when your boss thinks things happen. Your boss's body has experienced 3 hours of sleep. This is not just his mind saying, oh, well, a message says that it was 3 hours. No, every molecule in your boss's body has experienced 3 hours of time between when you sent the message and so when he sent the message and when your reply arrived, all right? Every cell has undergone 3 hours of whatever biochemistry happens when you're asleep. Every neuron in the brain has experienced 3 hours of sleep. The body has undergone all the regenerative effects of 3 hours of sleep, and it will undergo all the negative effects of being interrupted after only 3 hours of sleep. All right, so this is according to every molecule, every chemical reaction, every single physical fact of experience, 3 hours. Now, if there are no questions on that, let's switch to the next topic from chapter 4, which is called proper time. The proper time between two events is the time measured by an observer who's present at both events. So I shouldn't say the proper time, I should say a proper time, because there are lots of ways to be present at events 1 and 2 on this diagram. Events 1 and 2 happen roughly at the same spatial coordinates, so you could just stand still from time 1 to time 2 and look at your watch and see how much time elapsed. Someone else could go on a spaceship that first travels kind of slow away from point 1. We know it's traveling kind of slow because that world line is almost vertical, and then suddenly travels really, really fast to get back there. We know it's fast because that world line is at much more of an incline. Its slope is definitely closer to -1 in this case. They measure a proper time. Someone else could have gone at constant velocity half the way, then constant half the time, then back at constant velocity. These are all different proper times. So the fact that there are so many different proper times is why I hate calling it proper time, but we're stuck with the terminology. All right, so we're just going to focus on this person following this very curved world line. And although their velocity is changing, if I just watch them over a short instant, it doesn't change very much, all right? And the physical effect of that, that's not just me in my reference frame looking at it and saying, well, to me, all these changes are small, and so the only absolute is me. We know that that's not true in relativity. It's that if we were to do an experiment in this person's reference frame, in a short time interval, anything that they let go of, yeah, it's a non-inertial reference frame, so anything they let go of is going to change velocity, but it won't change velocity very much according to them in that time. And remember that in relativity, a small velocity change means small compared to the speed of light. It could be freaking huge. It could be going faster than the comet that wiped out the dinosaurs. That's still minuscule compared to the speed of light. All right. So in this little segment of the world line, I could compute the proper time between these two events along that world line by assuming that the velocity hasn't changed much. So for this short time interval, it seems like it's almost an inertial reference frame, right? You can make that approximation. We're making the same approximation we make in calculus, where we say something's almost linear between 2 points. Of course, a curve, most curves aren't really linear, but we're pretending that it's almost linear going from here to there. So we take delta TAB squared and delta XAB squared, take the difference between those, you take the square root. Now, what we then do is we say, okay, well, delta XAB is going to be V delta TAB. And so we get V squared, delta T squared here. We got delta T squared in both terms, so we can factor it out. And we're left with delta T square root of 1 minus V squared. And square root of 1 minus V squared is something we're going to see over and over again in relativity. And the nice thing about V is that relative velocity is something we all agree on. Okay, it's one of the few things we agree on in relativity. Remember, in relativity, what are our objective truths? The speed of light is 1. We agree on our relative velocity up to a minus sign in the question of who's moving, and Galileo was a genius, at least as good as Einstein. Those are the 3 things we all agree on in relativity. All right? So then we could find the proper time between 2 events by just integrating square root of 1 minus V squared dt. And of course, in general, square root of 1 minus V squared will be changing. I mean, if we look here, V at this time is positive and small. Then it becomes positive and smaller. Positive and smaller still. Here, the world line is for a moment vertical, which means that for a moment, x isn't changing. So the speed is 0. Then the velocity is negative. It's getting large, which means V squared is non-zero and large, right? And the important thing is that this T1 and T2 have to be measured in an inertial reference frame. So this doesn't mean that the person on the spaceship can just take their own measurements and do whatever they want with them and get a proper time. The only way for the person on the spaceship to get a proper time is to look at their clock. That is the definition of a proper time. But if instead they look at velocity, well, their velocity measurements are going to be much more complicated. All right. Questions? I've thrown a lot at you. It's weird. I don't believe that nobody has a question. Somebody must have a question. Come on, somebody's got to have a question. Relativity is weird. How could you not have questions on relativity? If I go out in public and tell people I'm a physicist, I usually get one of two reactions. Either I get, oh man, physics was so hard. Oh man, you're too smart. Oh man, my high school physics class was so confusing. Oh man, I tried taking physics and I dropped it. I get that response. Or I get, oh yeah, I saw this special, this documentary on Netflix. Have you seen that? You know, that one special, the one on Netflix about science? Okay. Yeah, you know, that one special had that guy. And then they inevitably start asking me about quantum mechanics or relativity, because in that one special with, you know, that guy was talking about quantum mechanics or relativity. And, you know, you must know that special, it's that science show with that guy on it. So people are always asking me about relativity. Once I showed up for jury duty, and they went through the usual, so what do you do for a living? I said, I'm a physics professor at a state university. The judge is all of a sudden like, physics? Oh, the other day I saw this TV special about Einstein and relativity. I wish I was joking. But yeah, here we've got a trial. Some guy is being accused of something pretty serious. So either he's an innocent guy about to get screwed, or he's a super dangerous guy that we really need to lock up. Either of those are high stakes. And the judge wants to interrupt it to ask me about relativity. I'm not joking. So if the judge could have a question about relativity while someone is being accused of something pretty serious, surely you guys must have a question about relativity. Nobody? Well, I guess you're not cut out for careers as state judges then. Okay. I don't know how you're going to become a judge if you can't tell me about that one special with, you know, that guy. Okay, so let's talk about evidence for this. One of the most common pieces of evidence is that people do experiments all the time with muons. Muons are not just present in the atmosphere. Muons can be created at particle accelerators. And muons are pretty useful for a lot of experiments because even though they're short-lived, they're not nearly as short-lived as some of the subatomic particles out there. So 1.5 microseconds is a lot longer than some particles last. And also their mass, although 200 times the mass of an electron, is still less than the mass of almost anything else you can make in an accelerator. And by E equals mc squared, well, that's going to be how much energy you need to make a particle. We'll get to that soon enough. And so it's much easier to make muons. And because muons are so similar to electrons, you will actually find applied physicists who say, you know what I need? I need an experiment where I've got something that's just like an electron, only heavier. And I want to see how it behaves in the presence of these atoms in this solid, because I want to probe some fact about the atomic orbitals. So you will actually see people use muons for that. So people make muons all the time, and they can have them travel around in rings. And in rings, the proper time that they measure will be the time that you measure multiplied by the square root of the square root of v squared. Which means that the half-life in their frame, the time that they need to see elapse before they figure, okay, maybe half of us should decay now, is equal to the square root of 1 minus v squared multiplied by the half-life in your reference frame. So let's talk again about the twins paradox. All right, again, you're on Earth, your twin travels to a distant star. So to the person on Earth, the time that elapses is twice this distance over v, because the twin goes to the distant star, then realizes that they left their passport on Earth, and so they won't be able to clear customs, so they return to Earth. So 2L over v. But delta tau, the proper time measured by the twin, is 2L over v times the square root of 1 minus v squared. Now here's the trick. To some people, that alone is paradoxical enough. The two different people measured two different times. and they start off as twins, but one of them winds up looking older than the other. And to some people, that's paradox enough. But that we've already explained. Here's the thing for people who, well, explained is a strong word. That we've already gone through to the extent that anyone can explain relativity. Here's a paradox, or something that should be a little bit confusing for those who do know relativity, but are still in the process of really absorbing it. Your twin sees you traveling, okay? So as far as your twin is concerned, the person on Earth is initially moving away, and then they're moving back. And so shouldn't the twin be able to use their measurements and you figure out how much time elapses to according to the person on Earth? And so the twin could say, well, you know, all right, on my spaceship, here's how much time I measured. And the person on Earth was traveling at V relative to me. Sometimes V is positive, sometimes V was negative. Just take the measurements on the spaceship and multiply those by square root of 1 minus V squared. And so the twin on the spaceship, if we use this argument, should say that the time elapsed on Earth was even shorter. But this breaks down. This argument is wrong. And the reason this argument is wrong is that the twin is not in an inertial reference frame. The twin's velocity changes during this trip. And we know the twin's velocity changes during the trip because when the spaceship changes velocity, all of a sudden the twin's going to feel jerked around. Just like when a car speeds up, you feel thrown back, and when a car comes to a sudden stop, you get jerked forward. All right? So the twin, that is the twin's evidence that they were not, that's the evidence that the twin on the spaceship is not in an inertial reference frame. And therefore, the delta T that the twin on the spaceship measures cannot be used in this formula. Because in this formula, we're assuming that all of the quantities here were measured by someone in an inertial reference frame. And yes, they agree on the V, but what they don't agree on are the times. Questions? Anyone? All right, then I've got some questions for you. Okay. So let's say that we carefully synchronize two identical atomic clocks standing next to each other. And we put clock B on a jet plane, which then goes around the world at a roughly constant speed of 300 meters per second, returning 37 hours later. And we compare the two clocks. And by the way, this experiment has been done. People have put an atomic clock on an airplane, flown it around the world, and then verified that it measured a shorter time interval than an identical clock that was initially synchronized with it and left on the ground. So, two questions to start with. Which clock measures the space-time interval between the synchronization event, the event that happened right before they parted ways, and the comparison event, when they met up with each other again? Give you a moment to think about that. And then since I haven't set up software for voting on this, I'll just reveal the answer. Where's my clock A measures the space-time interval because clock A is in an inertial frame. It's on the ground, and yes, technically the ground is moving, but the ground is moving slowly relative to the plane. And which one measures a coordinate time? Well, again, clock A, the one on the ground, because coordinate time and space-time interval are measured are quantities measured in an inertial frame. But the shorter time interval will be the one on the plane because it was moving relative to an inertial frame. Any questions on that? Okay, then in that experiment, what is the minimum accuracy that the clocks need in order to display this effect? Remember, it's going at 300 meters per second. 300 meters per second, 3 times 10 to the second, whereas the speed of light is 3 times 10 to the 8th. So this is at 1/1,000,000th the speed of light. It's at 1/1,000,000th the speed of light, and this took about 100,000 10 to the 5th seconds. The answer is 10 nanoseconds, and I want to work that out. Wait, screen, share my screen, go into OneNote. I want to work that out with you. Oh, wait, that was a joke I was writing up earlier. And why is that showing up in my lecture notes? That really shouldn't be showing up in my lecture notes. Did I delete all those pages? Oh, it's just taking forever. Okay. All right. So, delta tau is delta t, roughly 10 to the 5th seconds, multiplied by square root of, Jesu Christo Gil, by square root of 1 minus v squared. All right, well, what we know is that 1 plus x to the n is roughly 1 plus nx. And in this case, we've got that n is a half and x is minus v squared. So this is going to be 1 minus v squared over 2. All right? So this is going to be 1 minus 10 to the minus 6 squared over 2. All right, so our discrepancy, the difference between the clocks, delta t minus delta tau, will be delta t minus delta t times 1 minus v squared over 2, or delta t over 2 times v squared, or 1.3 times 10 to the 5th seconds multiplied by 10 to the minus 12, because v was 10 to the minus 6 over 2. So we're going to have 0.65 times 10 to the minus 7 seconds, or about 6.5 times 10 to the minus 8 seconds. Any questions on how I did that? Anyone? No questions? All right, so we've got a discrepancy of 10 to the minus 8 seconds. In order to detect the discrepancy of 10 to the minus 8 seconds, we had better have an accuracy of about 10 to the minus 9 seconds, all right, which is 10 nanoseconds. And that's a very achievable timing accuracy for an atomic clock these days. It has been for a while. Okay, another scenario. Somebody bungee jumps from a bridge. So they leave the bridge at event A. Their bungee cord is perfectly elastic, so she bounces straight back up and lands on her feet, event B. And the time between these events is measured by her watch. It's also measured by a stopwatch held by her friend who is standing on the bridge, and two passengers who are going at constant velocity along the bridge. And so, first question, who measures the longest time interval between these events? Who measures the shortest time interval? And who measures the space-time interval? Longest, shortest, and space-time interval. The longest time interval is measured by the passengers, okay? And the way to think about that is that the space-time interval is itself a type of coordinate time, all right? But, wait, I never showed you, Christ. I never showed you this, did I? Oops, okay. All right, so the way to think about that is that delta S is the square root of delta t squared minus delta x squared, right? Or delta S squared is delta t squared minus delta x squared. So delta t squared, coordinate time, is delta S squared plus delta x squared. All right? These are all coordinate times. This delta S is another coordinate time. But delta S is the coordinate time that someone measures if they're present at both events. Delta T is any coordinate time, including possibly a coordinate time in which somebody was present at one event and not present at the other. All right, so there's these people on the train. Well, maybe they happen to line up with the bungee jumper at one of those events, but they definitely didn't line up with the bungee jumper at the other event. So these two events are spatially separated in their reference frame. So the train passengers, they measure a coordinate time, and it's going to be longer than the space-time interval, which is the shortest possible coordinate time. It's also a proper time. In fact, it's the longest possible proper time. So if we have 3 observers, 2 of whom are measuring coordinate times, and one of those 2 is measuring space-time interval, 2 of whom are measuring proper time, and one of them is measuring a space-time interval, then the people who are measuring coordinate time but not space-time interval will measure the longest time. The person who's measuring space-time interval will measure something intermediate, and the person who's only measuring proper time will measure the shortest of the 3 time intervals. Questions? Anyone? Anyone? Then let's do a few more of those clicker questions. Let me switch my screen back. Okay. In the situation described in the previous problem, the train passengers are moving, but Rob, the guy on the bridge, is at rest. Therefore, the train passengers must measure less time. True or false? Now, this one we already discussed. We already established why the people on the train are measuring a longer time. So I'm not going to expect you to select true or false. We already know that they measure a longer time, not a shorter time. But it is important to push back on this one because we've been doing all these scenarios that build up your intuition that, hey, the person standing at rest on the ground is measuring this long time. And the people who are moving, like in the twins paradox, they're measuring a short time, or the person in the lab is measuring a long time, whereas that high-speed muon is measuring a really short time. All right? But in all of those cases that we've done where the observer who we say is moving is measuring a really short time, and the person that we say is standing still is measuring a really long time, all of those observers are present at both events. You know, the muon may be going in a circle, but it's present when it departs and it's present when it returns. The twin may be going back and forth, all right, but the twin is present when they say goodbye on Earth, and the twin is present when they're reunited on Earth, all right? So we've always been talking about these moving observers measuring really short time. If we try to then start saying, hey, the train passengers are moving, so they must measure a really short time. Well, in relativity, there's no real notion of who's actually moving and who's actually standing still. Those notions of actually moving or actually standing still don't make any sense. So the observers who we call moving, what we should really be saying is that those observers were in non-inertial reference frames. And so they were able to observe really short time frames between events. All right? Whereas the observers in inertial frames measured much longer time frames between events. All right, another scenario. We synchronize 2 atomic clocks at a point at 45 degrees south, and then we move one of them to the equator and the other to the South Pole. And they spend some years in climate-controlled enclosures, same temperature, same humidity, so the clocks aren't going to malfunction or get out of sync. We then reunite the clocks at the origin and compare them again and assume that everything has moved at the same speed. All of these motions to move clocks apart from each other and then back together were slow and done at the same speed. Clock at the equator, because the clock at the equator was moving, right? So the clock at the equator was in a non-inertial reference frame because its velocity keeps changing, right? Speed doesn't change, but its velocity or direction of its velocity keeps changing, which means its velocity changes. It's in a non-inertial frame. Whereas the clock at the South Pole, that clock was standing still for the entire thing, except that part where they were moved along the surface of the Earth. But once one of them reached the equator and the other one reached the South Pole, then the clock at the South Pole got to be in an inertial frame. You might say, well, not according to observer on the sun. Well, yeah, but those effects are the same for both the person at the equator and the person at the South Pole. Any questions? Okay. So GPS satellites, they go around the Earth. And the question is, after 24 hours, if we ignore gravity, and we're going to learn at the end of the semester that we can't ignore gravity. But if we were to just separate out effects, and for now we're only considering the fact that the clock that's on the satellite is going at is going around the Earth, and it's going around pretty fast, then what would be the time discrepancy? Now, I'm not going to ask everyone to pull out calculators because I do want to get to one example, but I'll just show you the answer here. The clock's orbital speed would be the circumference of the Earth, the circumference of the orbit, excuse me, 2 pi times the radius of the orbit divided by the orbital period, all right? And that's the speed, and it's about 1.3 times 10 to the minus 5, the speed of light. Then we could calculate the discrepancy between the clocks on the ground and the clock in orbit by calculating square root of 1 minus v squared. And we get roughly 7.2 microseconds. So that is at a minimum, that's like that's the minimum accuracy needed. In principle, we need much better accuracy than that. But just to account for relativistic effects, we need something that's at least that accurate. Any questions? Then I want to do 1 or 2 more problems. Let's start with this one. We've got a muon that is approaching the ground at 0.9998 times the speed of light. And it travels 10 kilometers in the atmosphere. So the time that it takes to reach the ground, according to us on the ground, watching it travel 10 kilometers in 10 kilometers at that speed is 33 microseconds. But the proper time measured by the muon is 33 microseconds, square root of 1 minus v squared, right? So according to the muon, it took 0.66 microseconds for the ground to reach it. Because remember, as far as the muon is concerned, it's not moving. The ground is moving. So the muon says that this ground traveled towards it in 0.66 microseconds. All right. So far, this is just a plug and chug of things we've been doing. But the muon sees the ground traveling at this speed, and it thinks that this amount of time has elapsed. So if we were to figure out how far the muon thinks the ground moved, it would say, well, 0.66 microseconds multiplied by that speed is 200 meters. So the muon thinks that the ground traversed the atmosphere by going a distance of 200 meters, which means that the muon thinks that the atmosphere is actually much smaller. So what I want you to take away from this example is we've been calculating all of these different times using these square root of 1 minus v squared factors. But we keep on saying that both observers in the theory of relativity agree on the relative velocity. They could disagree on everything else, but they agree on their relative velocities. Well, if they do, then they have to disagree on distance traveled, because they disagree on the time that was elapsed, but they agree on the relative velocity. So they must disagree not just on the sign of the displacement vector, not just on the question of whether one of them moved left or the other one moved right, who moved left, who stood still and who moved, and if they moved, did they go left or right? They have to actually disagree on how far someone went. And that means that we're going to need equations that we can use to calculate changes in distance. And that's going to be what we do next time. We're going to develop the Lorentz transformation equations and talk about how space also contracts along with time. Any questions? Anyone? Pretend you're a district court judge in the middle of jury selection. For those who logged in late, I was saying that people always ask me questions about relativity. Once I got called for jury duty, when I was asked to state what I do for a living, I told them. The judge started asking me physics questions about relativity. So somebody must have a question about this. I don't believe that there are no questions.
Professor, for this problem, when you set the muon, it sees the Earth moving towards it or the ground towards it.
Yeah.
Does that relate to the paradox of the barn and the stick?
That is related, and we will get to that on Friday.
Oh, okay.
Anyone else? All right. Have a good day. Class is over.